Indeed, there's a few improvements I want to make, so let me actually do those right now. Technically, I should practice what I preached, and I should indeed, when I'm done with t, free t. Fortunately, I don't have to worry about how big t was. The computer remembers how many bytes it gave me, and it will go free all of them, not just the first. I should do free t. I don't need to do free s, and I shouldn't, because that is handled automatically by the CS50 library. S, recall, came from getString, and we actually have some fancy code in place that makes sure that at the end of your program's execution, we free any memory that we allocated, so we don't actually waste memory like I described earlier. But there's actually a couple of other things, if I really want to be pedantic, I should put in here. It turns out that sometimes malloc can fail. And sometimes malloc doesn't have enough memory available, because maybe your computer is doing so much stuff, there's just no more RAM available. So technically, I should do something like this. If t equals null with two L's today, then I should just return 1 or something to say that there was a problem. I should probably print an error message too, but for now, I'm going to keep it simple. I should also probably check this. This is a little risky of me. If I'm doing t bracket 0, this is assuming that there is a letter there. But what if the human just hit enter at the prompt and didn't even type h, let alone hi exclamation point? What if there is no t bracket 0? So technically, what I should probably do here is, if the length of t is at least greater than 0, then go ahead and safely capitalize the first letter of it. And then at the very end, if all goes well, I can return 0, thereby signifying that indeed this thing was successful. So yes, these two functions, malloc and free, should be in concert. And so if you call malloc, you should call free eventually. But you did not call malloc for s, so you should not call free for s. All right, yeah, other question. Why did I do malloc plus 1? So malloc of string length of s plus 1. The string length is sort of the literal length of the string as a human would perceive it in English. So hi exclamation point, strlen gives me 3. But I know now, as of last week and this week, what a string technically is. And a string always has an extra byte. The onus is on me to understand and apply that lesson learned so that I actually give strcpy enough room for that trailing null character. And here's just an annoying thing. When we call the \0 NUL last week, it turns out that NULL is the same idea. It's also 0, but it's 0 in the context of pointer. So long story short, you never really write NUL. I've just said it, and we saw it on the screen. You will start writing NULL when you want to check whether or not a pointer is valid or not. And what I mean by that is this. If malloc fails and there's just not enough memory left inside of the computer for you, it's got to return a special value. And that special value is NULL in all capital letters. That signifies something went wrong. Do not trust that I'm giving you a useful return value. Other questions on these copies thus far? Yeah, over there. Good question. Will strcpy not work without malloc? You kind of need both in this case, because strcpy, by definition, if I pull up its manual page, needs a destination to put the copied characters. It's not sufficient just to say char star t semicolon. That only gives you a pointer. But I need another chunk of memory that's just as big as hi exclamation point \0. So malloc gives me a whole bunch of memory. And then strcpy fills it with hi exclamation point \0. So again, that's why we're sort of going down to this lower level, because once you understand what needs to be done, you now have the functions to do it. So let's actually consider what we just solved. So in this SNCS version of the program where I actually introduced malloc, t was initialized to the return value of malloc. And maybe the memory that I got back was here, 0x456, 457, 458, 459. I've left it blank initially because nothing is put there automatically by malloc. I just get a chunk of memory that is now mine to use as I see fit. I then assign t to that return value, which points t at the first address. Notice there's no \0. This is not yet a string. It's just a chunk of memory. 4 bytes, an array of 4 bytes. What strcpy eventually did for me was it copied the h over, the I over, the exclamation point over, and the \0. And if I didn't want to use strcpy, or I forgot that it existed, my for loop would have done exactly the same thing. All right, any questions then on these examples here? Any questions? Yeah? Good question. After malloc, if I had then still done just t equals s, it actually would have recreated the same original problem by just copying OX123 from s into t. So then I would have been left with a picture that looked like this a few steps ago. I would have, and I can't quite do it live, this arrow, if I did what you just described, would now be pointing over here. And so I wouldn't have fundamentally solved the problem. I would have just additionally wasted 4 bytes temporarily that I'm not actually using. Yeah? Do you always use malloc and strcpy together? Not necessarily. These are both solving 2 different problems. Malloc's giving me enough memory to make a copy. Strcpy's doing the copy. However, you could actually use an array if you wanted of characters, and you could use strcpy on that. And there's other use cases for strcpy. But thus far, it's a reasonable mental model to have that if you want to copy strings, you use malloc and then strcpy, or your own homegrown loop. Yeah? Say that once more. If you wanted to copy the last character of s, would the computer just fill in the last box? No, it will. Good question. If I strcpy per its documentation will copy the whole string plus the null character at the end. It just assumes there will be one there. It's therefore up to you to pass strcpy a long enough chunk of memory to have room for that. If I only asked malloc for 3 bytes, that could have potentially created a memory problem whereby strcpy would just still blindly copy 1, 2, 3, 4 bytes. But technically, it should have only touched 3 of those. You do not yet have access to the 4th one or the rights to it because you never asked malloc for it. Yeah. Correct. The number inside malloc, it's 1 argument, is the number of bytes you want back. Yes, the onus is on you, the programmer, to remember or frankly use a function to figure out how many bytes you actually need. That's why I did not ultimately type in 4 manually. I used strlength plus 1. So the plus 1 is necessary if you understand how strings are represented. But using strlang means that I can actually play around with any types of inputs, and it will dynamically figure out the length. So suffice it to say, there's so many ways already where you can start to break programs. Let's give you at least one tool for finding mistakes that you might make. And indeed, in upcoming problem sets, will you use this to find bugs in your own code? Not just using printf, not just using the built-in debugger, but another tool here as well. So let me go ahead and deliberately write a program called memory.c that has some memory-related errors. Let me include standardio.h at the top, and let me include standardlib.h at the top, so I have access to malloc now. Let me do int main void, and then inside of main, let me do this. I want to allocate maybe, how about space for 3 integers. Why? Just for the sake of discussion. So I'm going to go ahead and do malloc of 3, but I don't want 3 bytes. I want 3 integers, and an integer is 4 bytes. So technically, I could do this, 3 times 4. Or I could do 12. But again, that's making certain assumptions. And if I run this program on a slightly different computer, ints might be a different size. So the better way to do this would be 3 times whatever the size is of an int. And this is just an operator you can use anytime if you just want to find out on this computer how big is an int, how big is a float, or something else. So that's going to give me that much memory for 3 ints. What do I want to assign this to? Well, malloc returns an address. Pointers are addresses, so I'm going to create a pointer to an int called x and assign it the value. So what am I doing here? This is a little less obvious, but again, go back to basics. The right-hand side here gives me a chunk of memory for 3 integers. Malloc returns the address of the first byte of that chunk. How do I store the address of anything? I need a pointer. The syntax for today is type of data star. The type of data in question is 3 ints, so I do int star x. Again, it's kind of purposeless, only for sort of instructional purposes here. But this is equivalent now to having a chunk of memory of size 12 in total, presumably. So I can technically now do this. I can go into maybe the first location and assign it the number 72, like the other day. Second location, the number 73. And the third location, maybe the number 33. Now, I've deliberately made 2 mistakes here because I'm trying to trip over my newfound understanding or my sort of greenness with understanding pointers. One, I didn't remember that I should be treating chunks of memory as 0 indexed. malloc essentially returns an array, if you want to think of it as that. An array of 3 ints, or more technically, the address of a chunk of memory that could fit 3 ints. So I can use my square bracket notation, or I could be really cool and use pointer arithmetic, but this is a little more user-friendly. But I have made 2 mistakes. I did not start indexing at 0. So line 7 should have been x bracket 0. Line 8 should have been x bracket 1. And then line 9 should have been x bracket 2. So first mistake. The second mistake that I've made as a side effect is I'm also touching memory that I shouldn't. X bracket 3 would mean go to the 4th int in the chunk of memory that came back. I only asked for enough memory for 3 ints, not 4. So this is what's called a buffer overflow. I am accidentally, but deliberately at the moment, going beyond the boundaries of this array, this chunk of memory. So bad things happen, but not necessarily by just running your program. Let me go ahead and just try this. Make memory. And you'll see here that it compiles OK, /memory. And it actually does not segmentation fault, which comes back to that point of non-determinism. Sometimes it does, sometimes it doesn't. It depends on how bad of a mistake you made. But there's a program that can spot these kinds of mistakes. And I'm going to go ahead and expand my terminal window for a moment. And I'm going to run not just /memory, but a program called valgrind /memory. This is a command that comes with a lot of computer systems that's designed to find memory-related bugs in code. So it's a new tool in your toolkit today, and you'll use it with the coming problem sets. I'm going to run this now. Its output, honestly, is hideous. But there's a few things that will start to jump out and will help you with tools in the problem set to see these kinds of things. Here's the first mistake. Invalid write of size 4. That's on memory.c line 9 per my highlights. So let me go look at line 9. In what sense is this an invalid write of size 4? Well, I'm touching memory that I shouldn't, and I'm touching it as though it's an int. And an int is 4 bytes, size 4. So again, this takes some practice to get used to, the nomenclature here. But this is now a clue for me, the programmer, that not only did I screw up, but I screwed up related to memory. And so this is just kind of a hint, if you will. It's not going to necessarily tell you exactly how to fix it. You have to kind of wrestle with the semantics. But invalid write of size 4, oh, OK. So I should not have indexed past the boundary here. All right, so I shouldn't have done that. So let me go ahead then and change this to 0, 1, and 2 perhaps here. All right, so let me go ahead and recompile my code, make memory. /memory still doesn't seem to be broken, but it is technically buggy. Let me go ahead and run valgrind again. So valgrind of /memory, enter. And now there's less scary output now, but there's still something in there. Notice this. 12 bytes in 1 blocks, no regard for grammar there, are definitely lost in loss record 1 of 1. Super cryptic, but this is hinting at a so-called memory leak. The blocks of memory are lost in the sense that I malloced them. I asked for them, but I never, take a guess, freed them. I have a memory leak. And this is the arcane way of saying you've screwed up, you have a memory leak. So this is an easy fix, fortunately. Once I'm done with this memory, I just need to free it at the end. So now let me go ahead and rerun make memory. It still runs fine. So all the while, I might have thought incorrectly my code is correct. But let me run valgrind one more time. Valgrind of /memory, enter. Now, this is pretty good. All heap blocks were freed, whatever that means. No leaks are possible. And even though it's still a little cryptic, there's no other error here. And in fact, it's pretty explicit. Error summary, 0 errors from 0 contexts, .. So even though this is one of the most arcane tools we'll use, it's also one of the most powerful because it can see things that you, the human, might not, and maybe even that the debugger might not. It does a much closer reading of your code while it's running to figure out exactly what is going on. All right, any questions then on this tool? And we'll guide you after today with actually using this too. Just helps you find memory-related mistakes that you might now be capable of making. All right, let's do one other memory-related thing. Let me shrink my terminal window here. Let me create one other file here called garbage.c. So it turns out there's a term of art called garbage values in programming that we can reveal as follows. Let me include standardIO.h, and let me include, how about standardlib.h. And then let me give myself int main void. And then in this relatively short program, let me give myself like 3 ints using last week's notation, just int scores bracket 3 for like 3 quiz scores or whatever. Then let me go ahead and do for int I equals 0, I less than 3, I plus plus. Then let me go ahead and print out %i backslash n scores bracket I, semicolon. That's it. This code, pretty sure, is going to compile, and it's going to run. But what is my logical bug? I've sort of forgotten a step, even though the code that's written is not so wrong. Yeah? Yeah, I didn't provide the scores. So I didn't actually initialize the array called scores to have any scores whatsoever. What's curious about this, though, is that the computer technically doesn't mind. Let me go ahead and sort of playfully make garbage, enter. And it's kind of an apt description, because what I'm about to see are so-called garbage values. When you, the programmer, do not initialize your code's variables to have values, sometimes who knows what's going to be there. The computer's been doing some other things. There's a bit of work that happens even before your code runs in the computer. So there might be remnants of past ints, char, strings, floats, anything else in there. And what you're seeing is those garbage values, which is to say you should never forget, as I just did, to initialize the value of some variable. And this is actually pretty dangerous. And there have been many examples of software being compromised because of one of these issues where a variable wasn't initialized. And all of a sudden, users, maybe, people on the internet in the context of web applications, could suddenly see the contents of someone else's memory, or remnants, maybe someone's password that had been previously typed in, or some other value like a credit card number that had been previously typed in. There are different defense mechanisms in place to generally make this not so likely. But it's certainly very possible, at least in this kind of context, to see values that you probably shouldn't, because they might be remnants from something else that used them. So this is to say, again, you sort of have this great power now to manipulate memory, but also now you have this great sort of hacking ability to poke around the contents of memory. And this is exactly what hackers sometimes do when trying to find ways to exploit systems. Are any questions here? No? All right, let's go ahead and take a quick 5-minute break. And when we come back, we'll build on these final topics. See you in 5. We are back. First, just a little programmer humor from XKCD, which hopefully now will make a little bit of sense to you. And what we'll also do next is take a look at a short 2-minute video that animates, with claymation, if you will, from our friends at Stanford, exactly what happens now if you have an understanding of what garbage values are and how they get there, and what happens then if you misuse them. It's one thing just to print them out, as I just did. It's another if you actually mistake a garbage value for a valid pointer, because garbage values are just zeros and ones somewhere, numbers, that is. But if you use that new dereference operator, the star, and try to go to a garbage value, thinking incorrectly that it's a valid pointer, bad things can happen. Computers can crash, or more familiarly, segmentation faults can happen. So allow me to introduce, if we could dim the lights for 2 minutes, our friend Binky from Stanford.
Hey, Binky, wake up. It's time for pointer fun. What's that? Learn about pointers. Oh, goody! Well, to get started, I guess we're going to need a couple pointers. Okay. This code allocates 2 pointers which can point to integers. Okay, well, I see the 2 pointers, but they don't seem to be pointing to anything. That's right. Initially, pointers don't point to anything. The things they point to are called pointees, and setting them up's a separate step. Oh, right. I knew that. The pointees are separate. So how do you allocate a pointee? Okay, well, this code allocates a new integer pointee, and this part sets x to point to it. Hey, that looks better. So make it do something. Okay, I'll dereference the pointer x to store the number 42 into its pointee. For this trick, I'll need my magic wand of dereferencing. Your magic wand of dereferencing? That's great. This is what the code looks like. I'll just set up the number and... Hey, look, there it goes. So doing a dereference on x follows the arrow to access its pointee, in this case to store 42 in there. Hey, try using it to store the number 13 through the other pointer, y. Okay, I'll just go over here to y and get the number 13 set up, and then take the wand of dereferencing and just... Whoa! Oh, hey, that didn't work. Say, Binky, I don't think dereferencing y is a good idea because, setting up the pointee is a separate step, and I don't think we ever did it. Good point. Yeah, we allocated the pointer y, but we never set it to point to a pointee. Very observant. Hey, you're looking good there, Binky. Can you fix it so that y points to the same pointee as x? Sure, I'll use my magic wand of pointer assignment. Is that going to be a problem like before? No, this doesn't touch the pointees. It just changes one pointer to point to the same thing as another. Oh, I see. Now y points to the same place as x. So wait, now y is fixed. It has a pointee. So you can try the wand of dereferencing again to send the 13 over. Okay. Here goes. Hey, look at that. Now dereferencing works on y. And because the pointers are sharing that one pointee, they both see the 13. Yeah, sharing, whatever. So are we going to switch places now? Oh, look, we're out of time. But
It's from our friend Nick Parlante at Stanford. So let's consider what Nick did here as Binky. So here's kind of all the code together. These first couple of lines were not bad. And notice that in Stanford's code, they moved the stars to the left. That's fine. Again, more conventional might be this syntax here. These two lines are fine. It's OK to create variables, even pointers, and not assign them a value initially, so long as you eventually do. So we eventually do here with this line. We assign to x the return value of malloc, which is presumably the address of something. To be fair, we should really be checking for null as well, but that's not the biggest problem here. The biggest problem is not even this next line, which means go to the memory location in x and store the number 42 there. That's fine, because again, malloc returns the address of some chunk of memory. This chunk of memory is big enough for an int. X is therefore going to store the address of that chunk that's big enough for an int. Star x, recalls the dereference operator means go to that address and put 42 in it. It's like going to the mailbox and putting the number 42 in it instead of taking the number 50 out like we did before. But why is this line bad? This is where Binky sort of lost his head, so to speak. Why is this bad? Yeah. Exactly. We haven't yet allocated space for y. There's no mention of malloc. There's no assignment of y even to that same memory. So this would be go to the address in y. But if there is no known address in y, it is a so-called garbage value, which means go to some random address that you have no control over. And boom, that might cause what we've seen in the past perhaps as a segmentation fault. Now, this fortunately is the kind of thing that if you don't quite have the eye for it yet, Valgrind, that new tool, could help you find as well. But it's just another example of, again, the sort of upside and downside of having control now over memory at this level. All right, well, let's go ahead and do one other thing. Considering from last week that this notion of swapping was actually a really common operation. We had all of our volunteers come up. We had to swap a lot of things during bubble sort and even selection sort. And we just kind of took for granted that, the two humans would swap themselves just fine. But there needs to be code to do that if you actually implement bubble sort, selection sort, or anything that involves swapping. So let's consider some code like this. We'll keep it simple like last week and where we wanted to swap some values like int a and int b. For instance, here, void, because I'm not going to return a value, but I have a function called swap. So here, for instance, might be some code for this. But why is it so complicated here? Let's actually take a step back. Why don't we do this here? I think we have time for one more volunteer. Could we get someone to come on up? You have to be comfy on camera. And you're being asked to help with your friend. Oh, I'll go with the friend pointing. So whoever has their friend doing this here. No? Now they're pointing over here. Now literally an arm is being twisted. OK. Come on down. That backfired. Come on over. And what is your name? Marina? Yeah. Nice to meet you. Who were you trying to volunteer?
My friend Jessica.
OK. So here we have for Marina 2 glasses of liquid, orange and purple, just so that they're super obvious. And suppose that the problem at hand, like last week, is just to swap 2 values, like as though these 2 glasses represented 2 people, and we want to swap them. But let's consider these glasses to be like variables or location in an array. And you know what? I'd really like you to swap the values. So like orange has to go in there, and purple has to go in there. How would you do it? And we'll see if we can then translate that to code. OK, what did you say it a little louder?
I would put it in a different
All right, yeah. So presumably you're sort of struggling mentally with how you would do this without having an extra cup. So good foresight here. Let me go ahead, and we do have a temporary variable, if you will. So if I hand you this, how would you now solve this problem?
Well, I would go like that, but it's easy.
No, that's, oh, well, OK, do it. Go with your instincts. OK.
Put there and
Sure, go ahead. Go to whatever your instincts are.
spill.
Yeah, so strictly speaking, probably shouldn't have moved the glasses just because that would be like moving the array locations. So let's actually do it one more time. But the glasses now have to go back where they originally are. So how would you swap these now using this temporary variable? OK, good. Otherwise, we'd be completely uprooting the array, for instance, by just physically moving it around. So you moved the orange into this temporary variable. Then you copied the purple into where the orange was. And now, presumably, excellent. The orange is going to end up where the purple once was. And this temporary variable, it's sort of some extra memory. It was necessary at the time, but not necessary ultimately. But a round of applause if we could. And thank you for doing that so well. So, right, the fact that it sort of instantly occurred to Mariana that like you need some temporary variable is a perfect translation to code. And in fact, this code here that we might glimpse now is reminiscent of exactly that algorithm, where A and B at the end of the day are the same chunks of memory. Just like the second time, the two glasses have to kind of stay put, even though we're physically lifting them, but they're going back to where they were. It's kind of like having two values, A and B, and you just have a temporary variable into which you copy A, then you change A with B, then you go and change B with whatever the original value of A was, because you temporarily stored it in this temporary variable, TMP. Unfortunately, this code doesn't necessarily work as intended. So let me go over to my VS Code here and open up a program called swap.c. And in swap.c, let me whip up something really quickly here with, how about include standard io.h, int main void. Inside of main, let me do something like int x gets 1, int y gets 2. Let me just print out as a visual confirmation that x is %i, y is %i, \n, plugging in x and y respectively. Then let me call a swap function that we'll invent in just a moment, swap x and y. And then let me print out again, x is %i, y is %i, \n, just to print out again what they are, because presumably I should see 1, 2 first, then 2, 1 the second time. Now, how is swap going to be implemented? Let me implement it exactly as on the screen a moment ago. So void swap int x, or let's call it int a for consistency, int b. But I could always call those anything I want. Int temp gets a gets b gets temp. So exactly as I proposed a moment ago, and exactly as Mariana really implemented it using these glasses of water. I need to now include my prototype as always, so nothing new there. And I'll just copy paste that up here. And now let's go ahead and run this. So make swap. So far, so good. Swap. X is now 1, y is 2. X is 1, y is 2. So there seems to be a bit of a bug here. But why might this be? This code does not, in fact, work, even though it obviously works in reality. Yeah? Good, and let me summarize. A and B do indeed have different addresses of x and y. And in fact, what happens when you call a function like this on line 11, calling swap, passing in x and y, you are calling a function by value, so to speak. And this is a term of art that just means you are passing in copies of x and y, respectively, and calling them a and b in the context of this function. But they're indeed copies. Now, technically, these names are local only. I could have called this x. I could have called this y. I could have changed this to x, this to y, this to x, and this to y. The problem would still remain. Just because you use the same names in one function as you do elsewhere, that doesn't mean they're the same. They just look the same to you. But indeed, swap is going to get copies of this x and y. And in this context, this scope, so to speak, x and y will be copies of the original. So for clarity, let me revert this back to a and b, just to make super clear that they're indeed different, albeit copies. But there's indeed a problem there. This function actually works fine. In fact, notice this. Let me go ahead and print out inside of this, printf, a is %i, b is %i, \n, and then I'll print a and b. And let me do that same thing at the beginning of this function before it does any work. Let me go ahead and rerun make swap. /swap, and this is promising. Initially, x is 1, y is 2. A is 1, b is 2, a is 2, b is 1, but then nope, x is 1, y is 2. So if anything, I've confirmed that the logic is right, Mariana's logic is right, but there's something about C. There's something about using one function versus another that's actually creating a problem here. The fact that I'm passing in copies of these values is creating this problem. So what in fact is going on? Well, again, inside of your computer's memory, there's these little chips, and we've been talking about them abstractly. It's just this grid of memory locations. It turns out that your computer uses this memory in a pretty conventional way. It's not just kind of random where it just puts stuff wherever is available. It actually uses like different parts of the memory for different purposes. And you have control over a lot of it, but the computer uses some of it for itself. And let's go ahead and zoom out from this and consider that within your computer's memory, what a computer will typically do is actually store initially all of the zeros and ones that you compiled in the top of your computer's memory, so to speak. So when you compile a program and then you run it with / whatever, or on a Mac or PC, you double click on it, the computer first, the operating system first, loads all of your program zeros and ones, aka machine code, into just one big chunk of memory at the top, so to speak. Below that, it stores global variables. Any variables you have created in your program that are outside of main and outside of any functions, generally at like the top of your file. Globals tend to go at the top there. Then there's this chunk of memory that's generally known as the heap. And we saw that word briefly in Valgrind's output. And then there's this other chunk of memory called the stack. And it turns out that up until this week, you were using the stack heavily. Anytime you use local variables in a function, they end up on the stack. Anytime you use malloc, that memory ends up on the heap. Now, as the arrow suggests, this actually looks like a problem waiting to happen, because if you use more and more and more heap and more stack, it's like, two things barreling down the tracks at one another. This does not end well. And that's actually a problem. If you've ever heard the phrase Stack Overflow or used the website, this is the origin of its name. When you start to use more and more and more memory by calling lots and lots of functions or using lots and lots of local variables, you use a lot of this stack memory. Or if you use malloc a lot and keep calling malloc, and never really or rarely calling free, you just use more and more memory. And eventually, these two things might overflow each other, at which point you're just kind of out of luck. The program will crash or something bad will happen. So the onus is kind of on you just to don't do that. But this is the design generally of what's going on inside of your computer's memory. Now, within that memory, though, there are certain conventions focusing on here the stack. And in fact, let me go over here with a marker and say that this represents like the bottom of my memory, ultimately. And so here, we have a whole bunch of wooden blocks, and each of these squares represents a byte of memory. And this, for instance, might represent 4 bytes altogether, good enough for an int or something like that. So in my original code that I wrote earlier, that is in fact buggy, what is in fact going on inside the swap function, we can kind of visualize it like this. When you run /swap, or any program for that matter, main is the first function to get called with a C program. And so I'm just going to label this bottom row of memory as main. And what were the two variables I had in main called in this code? Yeah. X and y. And each of those was an int, so that's 4 bytes. So it's kind of deliberate that I reserved a chunk of wood here that's 4 bytes. So let me just call this x, and I'm just going to write the number 1 in this box here. And then I had my other variable y, and I'm going to put the number 2 there. What happens when main calls swap like it does in this code here? Well, it has two variables of its own, a and b. And a initially is 1. And b is initially 2, but it has a third variable, temp, which is a local variable in addition to the arguments a and b that are passed in. So I'm going to call this temp, TMP, over here. And what is the value of temp? Well, we have to look back at the code. Temp initially gets the value of a. All right, the value of a was 1, so temp initially gets 1. That's step 1 in my 3-line program. OK, a equals b. So that is assigned from the right to the left of the b into the a. So b is 2. A is this, so let me go ahead and erase this and just overwrite that. So at this moment in the story, you have 2 copies of 2. So that's OK, though, because the third line of code says temp gets copied into b. So what's temp? 1 gets copied into b. So let me overwrite this 2 with a 1. And now what happens? Now, unfortunately, the code ends. Swap doesn't actually do anything with the result. And the problem in C is that I could have had a return value. I could go in there and change void to int, But which one am I going to return? The A or the B? The whole goal is to swap two values. And it seems kind of lame if you can't write a function to do something as common per last week's sorting algorithms as swapping two values. But what really happens? Well, even though when this program starts running, main is using this chunk of memory at the bottom in the so-called stack. And the stack is just like a cafeteria, a stack of trays. It grows up like this. Here's main's memory on the stack. Here's the swap function's memory on the stack. It's using 3 ints instead of only 2. What happens when the function returns, whether it's void or not? The sort of recollection that this is swap's memory goes away, and garbage values are left. So adorably, we get rid of these values here. And there's still data there. Technically, the numbers 1, 1, and 2 are still there in the computer's memory, but they no longer belong to us because the function has now returned. So they're still in there. And this is kind of an example visually of why there's other stuff in memory, even though you didn't put it there necessarily. Sometimes you did put it there. But now, once swap returns, you only should be touching memory inside of main. But we've never actually copied one value into main. We haven't returned anything, and we haven't solved this fundamentally. So how could we do this? Well, what if we instead passed into swap not copies of x and y, calling them a and b? What if they passed in breadcrumbs to x and y, sort of a treasures map that will lead swap to the actual x and to the actual y? Today, we have that capability using pointers. So suppose that we use this code instead. There's a lot of stars going on here, which is a bit annoying. But let's consider what it is we're trying to achieve. What if we pass in not x and y, but the address of x and the address of y, respectively? Breadcrumbs, if you will, that will lead swap to the original values. Then what we do is we still give ourselves a temp variable, like an empty glass. It's still a glass, so we still call it an int. But what do we want to put into that temporary variable? We don't want to put a into it, because that's an address now. We want to go to that address, per the star, and put whatever's at that address. What do we then want to do? Well, we want to then copy into whatever's at location A. We want to copy over to location A's contents, whatever is at locations B's contents. And then lastly, we want to copy temp into whatever's at location B. So again, we're very deliberately introducing all of these stars because we don't want to change any of these addresses. We want to go to these addresses per the dereference operator and put values there or get values from. So what does this actually mean? Well, if I kind of rewind in this story and I go back here, I still have temp, although I'm going to delete its value to begin with. I still have B, and I still have A. But what's going to be different this time is how I use A and B. So let me finish erasing those. That's A on the left. This is B on the right. At this point in the story, we're rerunning swap with this new and improved version. And let's see what happens. Well, x is presumably at some address. Maybe it's like 0x123, as always. What then does A get when I'm using this code? The value of A is 0x123. What is the value of B? Maybe y is at 0x456. What goes in B? Well, I'm going to put 0x456. And then what am I going to do? Based on these 3 lines of code, I'm going to store in temp whatever is at the address in A. What is the address in A? That's this thing here. So I'm going to put 1 in temp. Line 2, I'm going to go to B. All right, B is 456. So I'm going to B. And I'm going to store 2 at whatever is at location A. And at location A is 1, 2, 3. So that's this. So what am I going to do? I'm going to change this one to a 2. Last line of code. Get the value of temp, which is 1. And then put it at whatever the location B is. So B, 456, go there. And change it to be the value of temp, TMP, which puts 1 here. That's it for the code. There's still no return value. Swap returns, which means these 3 temporary variables are sort of garbage values now. They can be reused by subsequent function calls. But now I've actually swapped the values of x and y, which is to say what came as naturally as the real world here for Mariana is not quite as simply done in C. Because, again, functions are sort of isolated from each other. You can pass in values, but you get copies of those values. If you want one function to affect the value of a variable somewhere else, you have to, 1, understand what's going on, but 2, pass things in as by a pointer here. So if I go back to my code here, I need to make a few changes now. Let me get rid of these extra printfs. Let me go in and add all these stars. So I'm dereferencing these actual addresses here and here, and I've got to make one more change. How do I now call swap if swap is expecting an int star and an int star? That is the address of an int and the address of another int. What do I change on line 11? Here, yeah. Sorry, a little louder. Sorry, the address of operator. So up here on line 11, we do ampersand x and ampersand y. So that, yes, we're technically passing in a copy of a value, but this time the copy we're passing in is technically an address. And as soon as we have an address, just like when I held up the fuzzy finger, or the foamy finger, I can point at that address. I can go to that address and actually get a value from the mailbox or put a value into the mailbox if I even want. So let's cross our fingers now and do make swap, enter. Oh my God, so many mistakes. Oh, I didn't remember to change my prototype. So let me go way up here and add 2 more stars, because I made that change already. Make swap, /swap, and voila, now I have actually swapped. Thank you. Thank you, the 2 values. All right, so what more can we do here? Well, let me consider that all this time we've been deliberately using getString and getInt and getFloat and so forth, but for a reason. These aren't just training wheels for the sake of like making things easier. They're actually in place to make your code safer. And to illustrate this, let me go ahead and open up one other file here. How about a file called code scanf.c? It turns out that the old school way, the way in C really, of getting user input is via functions like scanf. And let me go ahead and include standard.io.h, int main void, and without using the CS50 library at all for strings or for any of those get functions, let me give myself an int called x. Let me just print out what the value of x is, even though it's going to be, or rather ask the user for the value by asking them for x. And I'm going to use a function called scanf that's going to scan in an integer using %i. And I'm going to store whatever the human types in at this location. And then I'm going to go ahead and, just so we can see what happened, I'm going to print out with %i whatever the human typed in as follows. All right, so line 8 is week 1 style code. Line 5 and 6 is week 1 style code. So the curiosity today is this new line. Scanf is another function in standard.io.h. And notice what I'm doing. I'm using the same syntax that I use for printf, which is kind of a little clue, a format code to tell scanf what it is I want to scan in, that is, read from the human's keyboard. And I'm telling it where to put whatever the human typed in. I can't just say x, because we run into the same darn problem as with swap. I have to give a little breadcrumb to the variable where I want scanf to put the human's integer. And so this just tells the computer to get an int. This is what you would have had to type essentially in week 1 just to get an int from the user. And there's a whole bunch of things that can go wrong still, but that's the cryptic syntax we would have had to show you in week 1. Let me go ahead and make scanf here. Oops. User error. Put the semicolon in the wrong place. Make scanf. Enter. Oh my God. Non-void doesn't return a value. Oh, thank you. Start 2. OK. Make scanf. There we go. OK, so scanf, I'm going to type in a number like 50, and it just prints it back out. So that is the sort of traditional way of implementing something like getInt. The problem, though, is when you start to get into strings, things get dangerous quickly. Let me delete all of this and give myself a string s, although wait a minute, we don't call it strings anymore, char star to store a string. Then let me go ahead and just prompt the user for a string using just printf. Then let me go ahead and use scanf, ask them for a string this time with %s, and store it at that address. Then let me go ahead and print out whatever the human typed in just by using the same notation. So here, line 5 is the same thing as string s, but we've taken back that layer today, so it's char star s. This is just week 1. This is just week 1. Line 7 is new. Scanf will also read from the human's keyboard a string and store it at s. But that's OK, because s is an address. It's correct not to do the ampersand. It's not necessary. A string is and has always been a char star, AKA string. The problem, though, arises as follows. If I do make scanf, oh my God, what did I do wrong? Oh, I can't. OK, we have certain defenses in place with make. Let me do clang of scanf .c and output a program called scanf. All right, so I'm overriding some of our pedagogical defenses that we have in place with make. Let me now run scanf of this version, enter, and let me type in something like, how about hi again? Huh. So it didn't even store something, and it weirdly printed out null. This time it's in lowercase, but that is somewhat related. What did I fundamentally do wrong, though, here? Why is this getting more and more dangerous? And let me illustrate the point even more. What if I type in not just something like hello, which also doesn't work. What if I do like hello and make a really long string, enter. That still works. Can I do this again? Let's try again. All right, a really long, unexpectedly long string. This is the non-determinism kicking it. Enter. All right, damn it. I was trying to trigger a segmentation fault, but it wouldn't. But the point still remains. It's still not working. But what's the essence of why this isn't working and it's not storing my actual input? Yeah. We have to make space for it. So what we're missing here is malloc or something like that. So I could do that. I could do something like this. Well, let me let the human type in at least a 3-letter word. So I could do malloc of 3 plus 1 for the null character. So like, let me give them 4 characters. And let me go ahead and do make scanf. Whoops. Nope, sorry. Clang. I have to search. Nope. Damn it. Oh. Include standard lib.h. There we go. That gives me malloc. Now I'm going to recompile this with clang. Now I'm going to rerun it. And now I'm going to type in my first thing, hi. That now works. And let me get a little aggressive now and type in hello, which is too long. Still works, but I'm getting lucky. Let me try a hello. Damn it. That still works too. Sort of. But it actually, not quite. There's some weirdness going on there already. It turns out I could also do this. I could actually just say char star 4 and give myself an array of 4 characters. Let me try this one more time. So let me rerun clang /scanf. Hello, clearly exceeding the 4 characters. There we go. Thank you. All right, so the point here, though, is if we hadn't given you getInt, you would have had to use the scanf thing. Not a huge deal because it seemed to work. But if we hadn't given you getString, you would have had to do stuff like this, knowing about malloc already, or knowing about strings being arrays. And even now, there's a danger. If the human types in 5 letters, 6 letters, 100 letters, this code, like with the hello input, will probably just crash, which is bad. So getString also has this functionality built in where we have a fancy loop inside such that we allocate, using malloc, as many bytes as you physically type in. And we use malloc essentially every keystroke. The moment you type in H-E-L-L-O, we're sort of like laying the tracks as we go. And we keep allocating more and more memory so that we, theoretically, will never crash with getString, even though it's this easy to crash your code using scanf if you, again, did it without the help of a library. So where are we all going with this? Well, let me show you a few final examples that'll pave the way for what will be problem set 4. Let me go ahead and open up from today's code, which is available on the course's website. For instance, a program like this called phonebook.c. And I'm just going to give you a quick tour of it that you'll see more details on in the context of pset 4 itself. We're going to introduce a few new functions you're going to see. You're going to see a function called fopen, which stands for file open. And it takes 2 arguments, the name of a file to open, like a CSV that you might manipulate in Excel or Google Spreadsheets or the like, comma, separated values. And then something like A for append, R for read, W for write, depending on whether you want to add to the file, just open it up, or change it. We're going to introduce you to a file pointer. You'll see that capital file, which is a little non-conventional, capital file is a pointer to an actual file on the computer's hard drive so that you can actually access something like a CSV file or, heck, even images. And we're going to see down below that you're also going to have the ability to write files as well or print to files. You'll see functions like fprintf for file printf or fwrite, file write, which now that you will begin to understand pointers, you'll have the ability to actually not only read files, text files, images, other things, but also write them out. In fact, for instance, just as a teaser here, JPEGs will be one of the things we focus on this week, where we give you a forensic image, and your goal is to recover as many photographs from this forensic image of like a digital camera as you possibly can. And the way you're going to do that is by knowing in advance that every JPEG in the world starts with these 3 bytes, written in hexadecimal, but these 3 numbers. And so in fact, just as a teaser, let me open up an example you'll see on the course's website for today. If I scroll through here, you'll see a program that does a little something like this. And again, more on this in if we could, hit the button. Oh, there we go. So here we have the notion of a byte. We're going to create for ourselves, we'll see a data type called byte, which is a common convention. This gives me 3 bytes. And you're going to learn about a function called fread, which reads from a file some number of bytes, for instance, 3 bytes. We might then use code like this. If bytes bracket 0 equals OXFF, and bytes bracket 1 equals 0xD8, and bytes bracket 2 equals 0xFF, all 3 of those bytes I just claimed represent a JPEG, you'll see an output like this. Let me go ahead and run this program as follows. Let me copy jpeg.c into my directory from today's distribution. Let me do make JPEG. And let me run JPEG on a file, which is available online, called lecture.jpg. And I claim, yes, it's possibly a JPEG. Well, what is that file? Let me open it up for us, called lecture.jpg. And here, for instance, is that same photo with which we began class, namely implemented as a JPEG. But what we're also going to do this week is start to implement our own sort of filters a la Instagram, whereby we might take images and actually run them through a program that creates different versions thereof. For instance, using a different file format called BMP, which essentially lays out all of its pixels from left to right, top to bottom in a grid, you're going to see a struct, a data struct in C that's way more complicated than like the candidate structure from the past or the person structure from the past that looks like this, which is just a whole bunch more values in it. But we'll walk you through these in the P set. And we might take a photograph like this and ask you to run a few different filters on it, a la Instagram, like a black and white filter or grayscale, a sepia filter to give it some old school field, or a reflection like this to invert it, or blur it even in this way. And just to end on a note here, I have a version of this code ready to go that doesn't implement all of those filters. It just implements one filter initially. Let me go ahead and just ready this on my computer here. I'm going to go into my own version of filter. And you'll see a few files that we'll give you a tour of this coming week. In bitmap.h, for instance, is a version of this structure that I claimed existed a moment ago. And let me show you this file here, helpers.c, in which there is a function called filter that I've already implemented in advance today. But the ones we give you for the P set won't already be implemented. This function called filter takes the height of an image, the width of an image, and a 2-dimensional array. So rows and columns of pixels. And then I have a loop like this that iterates over all of the pixels in an image from top to bottom, left to right. And then notice what I'm going to do here. I'm going to change the blue value to be 0 in this case, and the green value to be 0 in this case. But why? Well, the image I have here in mind is this one, whereby we have this hidden image that simply has sort of old school style, a secret message embedded in it. And if you don't happen to have in your dorm like one of these sort of secret decoder glasses that essentially make everything red, getting rid of the green in the world and the blue in the world, you can actually, I'm actually probably the only one who can read this right now, see what message is hidden behind all of this red noise. But if using my code written here in helpers.c, I get rid of all the blue in the picture, and I get rid of all the green in the picture, essentially implementing the idea of this filter, this red filter where you only see red, well, let's go ahead and compile this program, make filter, run /filter on this hidden message.bmp. I'm going to save it in a new file called message.bmp. And with one final flourish, we're going to open up message.bmp, which is the result of having put on these glasses. And hopefully now you too will see what I see. All right. All right. All right, that's it for CS50. We'll see you next time.